Hello everyone. In this lecture, I am going to discuss about the time domain analysis. Subject is control system. This is useful for the electronics and communication engineering branch as well as for electrical engineering and electrical and electronics engineering branch. So, time response analysis of a system. So, time domain analysis refers to the analysis of the system performance with respect to the time. It is used to evaluate the system and state and the output responses with respect to the time. The time response of a control system usually refers and it is divided into the two parts, that is transient response and steady state response. Transient analysis is defined as a part of time response that goes to zero as time become very large, and in steady state analysis, basically steady state analysis is a part of the time domain response that remains after transient state has out. It deals with the estimation of the steady state between input and output. So, before discussing this transient state analysis and steady state analysis, you should know some standard inputs. These standard inputs are unit step signals, unit impulse signal, unit ramp signal, parabolic signals. So, unit impulse signal and unit step signal are used for sudden change, and ramp signal are used for constant velocity, and parabolic signals are used for constant acceleration. So, in general, control system design specifications are based on the response of the system to such test signals. So, there are it may be possible you can use the different signals, but this system has been tested on this standard signals that are available. So, these inputs are chosen because because they are capable of possible variations that can occur in any arbitrary signals. First is unit impulse signal. Mathematically, you can define as a delta t, and mathematically it is represented as minus infinite to infinite delta t is equal to 1 for, or you can write delta t is equal to 1 for t is equal to 0 and 0 t is not equal to 0 or elsewhere. Similarly, unit step signal is mathematically defined as, you can write here unit step signal is ut, here I have written xt is equal to 1 for t is greater than 0 and 0 for t is less than 0. So, what will be the value of at t is equal to 0? At t is equal to 0, this unit step signal shows abrupt discontinuity. So, this signal is not continuous at this or you can say this signal is not defined, or you cannot say about the amplitude at t is equal to 0. So, graphically we can draw the unit step signal like this. This is a unit step signal at t is equal to 0. Here it should be clear that this is attaining the amplitude 1 for t is greater than 0. This value is not at t is equal to 0. At t is equal to 0 plus amplitude is 1. What is the Laplace transform of this impulse signal? Laplace transform of this impulse signal is, your impulse signal is 1 and step signal is 1 by s. You can check, you can use this, use the Laplace transform formula for getting the Laplace transform of these standard signals. Ramp signal is represented as RT. RT is equal to AT for t is greater than or equal to 0 and 0 for t is less than 0. So, and the Laplace transform of this ramp signal is A by S square, and parabolic signal is xt is equal to at square by 2 for t is greater than 0, greater than or equal to 0, and 0 for t is less than 0, and the Laplace transform of this is A by S cube. So, these are the standard test signals which are used, which can be used in during the analysis of during the analysis of time domain analysis. There is a relation between step signal, ramp signal, and impulse signals. Impulse signal is the impulse signal is the derivative of step signal, and step signal is the derivative of ramp signal, or you can say similarly we can get by integrating the impulse signal and impulse signal and step signals. Now, what is the type and order of the system? Every transfer function representing the control system has certain type and order. The steady state analysis depends on the type of the system. The type of the system is obtained from the open loop transfer function GSHS. So, we can define the type of the system with the help of open loop transfer function, whereas for defining the order of the system we require the characteristic equation, that is 1 plus GSHS is equal to 0, or this number of open loop poles occurring at origin determines the type of the system. The transient analysis depends on the order of the system, and the order of the system is obtained from the closed loop transfer function. So, as I have already told you that this type of the system is obtained from the open loop transfer function, and the number of open loop poles occurring at origin will give the information about the type of the system, and order of the system can be found from the characteristic equations. Let us take an example for finding the type of the system. Suppose the open loop transfer function is given by this: GS is equal to k dash s plus z1 s plus z2 s ki power n s plus p1 s plus p2. So, here the number of poles occurring at origin, power of s will decide the type of the system. If n is equal to 0, then this is type 0 system, n is equal to 1, then this is type 1 system, n is equal to 2, then this is type 2 system, n is equal to 3, then this is type 3 system. Similarly, so first whenever you are going to find the type of the system, you have to find the value of, GS and HS. After finding the value of GS and HS, you can easily find the type of the system. Just you have to see the number of open loop poles occurring at origin, and the number of open loop poles will give the information about the type of the system. Let us take an example. GSHS is equal to K1 plus TAS upon S ki power P1 plus T1S, where P is equal to 0, type 0 system, P is equal to 1, type 1 system. Let us take this example. GS is equal to 10 S plus 2 upon S square S plus 5. So, here what will be the type of the system? Type will be equal to 2, and order, what will be the order? For finding the order of the system, you have to write the characteristic equation. What is the characteristic equation? Characteristic equation is 1 plus GSHS is equal to 0. So, GSHS is given to you, GS is given to you, and here they are saying that this is a unity feedback. It means HS is equal to 1. So, what will be the value of 1 plus GSHS? 1 plus GSHS will be this, and this will be the value of 1 plus GSHS. S cube plus 5s square plus 10s plus 2. Highest power of S will give the order of the system. So, what is the highest power of S in this characteristic equation? 3. So, you will get this type will be 3 and order will be 2. Now, coming to the transient response analysis. Consider this system, the following transfer function x naught s upon xis is equal to this. So, what will be the zero order system? When x naught s upon xis is equal to b naught by a1. And this zero order system is used in most of the sensor and transducers. And there is no time response of this zero order system because input and output characteristics are linear. Now coming to the first order system, it is clear from this equation that x naught s upon xis is equal to b naught upon a1s plus a naught. So you will get here, you can see here highest first order system, you have to find the order. So 1 plus GSHS is equal to 0. 1 plus TS is equal to power of S will give the type of the system, will give the order of the system. So this is the first order system. So you can also define here the time constant with the help of this equation by finding the value, by finding the step response. So the example of first order system is pneumatic system, hydraulic system and etc. System with only one pole are called first order system. Now coming to the first order system, the transient analysis of the first order system. So this is the transfer function, this is the standard canonical form of the closed loop system. Canonical form of the closed loop system means the transfer function, closed loop transfer function will be Ys by Rs will be equal to Gs upon 1 plus GSHS. This is the negative feedback system. Gs is equal to 1 by tau s upon s, 1 by tau s upon 1 plus 1 by tau s. So it will give 1 plus 1 tau s. So this is the transfer function. How will you find the response? You can find the impulse response as well as step response. So for finding the impulse response, you have to change the value of Rs. Here Rs will be equal to 1. So Ys will be equal to 1 by 1 plus tau s. So what will be, how will you find the response? You have to find the inverse Laplace of this Ys, which will give the value of Yt. By finding the inverse Laplace of this, we will get 1 by tau e ki power minus t by tau. So the response will be like this. You can see it. Next is step response. So here we have to take the step input. So what will be the value of Rs? Rs will be equal to 1 by s. So by putting the value of Rs, you will get this. Ys will be equal to 1 by s tau s plus 1. So by using the partial fraction, I will get 1 by s minus tau by 1 by tau s plus 1. So what will be the value of Yt? You have to find the you have to take the inverse Laplace of Ys. By taking the inverse Laplace of Ys, I will get 1 by s, Laplace inverse of 1 by s is 1, tau by tau s plus 1 is equal to e ki power minus t by tau. So the response will be like this, 1 minus e ki power minus t by tau. Now coming to the general equation of the second order system. This is the general equation of the second order system. Ys by Rs is equal to omega n square upon s square plus 2 zeta omega ns plus omega n square. Some parameters like natural frequency, damping factor, damping coefficients of any system, means mechanical system or electrical system, you have to just compare with this standard format. So suppose any mechanical system is given to you, for which the equation is given Td is equal to Jd square theta by dt square plus Bd theta by dt plus k theta. So TdS, take the Laplace transform of this, you will get here Js square plus Bs plus k theta s. What will be the transfer function? Theta s by TdS is equal to this. We have to compare with this, omega n square upon s square plus 2 zeta omega ns plus omega n square. So what will be the value of omega n? Omega n will be equal to under root k by j. What will be the value of 2 zeta omega n is equal to b by j. Just put the value of omega n, omega n in this equation, you will get the value of zeta. Similarly, we can find the value of omega n and zeta for this electrical system. So what will I do? I have to find the value of V naught upon Vi, transfer function. V naught output is V naught, input is Vi. So we will find the value of V naught upon Vi. For finding the value of V naught upon Vi, we will apply the KVL in this loop. After applying the KVL in this loop, we will get VIS is equal to R plus LS plus 1 by CS into IS, and V naught S is equal to 1 by CS into IS. So what will be the value of V naught by Vi? V naught upon Vi, V naught upon Vi will be equal to 1 by CS upon LCS square plus RCS plus 1 upon CS. This will be cancelled out and you will get 1 by LCS square plus RCS plus 1. So we have to convert this into a standard form, omega n square upon S square plus 2 zeta omega ns plus omega n square. So what will I do? I will make the coefficient of S square unity. So I will take LC common from this. I will take LC common, I will get here 1 by LC, S square plus R, S by L plus 1 by LC. So what will be the value of omega n? Omega n will be equal to under root 1 by LC. And what will be the value of zeta? You will find the 2 zeta omega ns, 2 zeta omega n is equal to R by L. So you will get here the value of zeta after putting the value of omega n in this equation. In this way we can find the natural frequency and damping coefficients. This is the standard form of second order system from where you can get the transfer function of the second order system. So here the forward path is omega n square upon S plus 2 zeta omega n, and feedback is 1. So from where you can get, again this is the standard or canonical form of the closed loop system. So here the forward path is this. You can write here GS upon 1 plus GS HS. So GS is equal to omega n square upon S plus 2 zeta omega n, and this is 1. So you will get this. So this is the standard form of the transfer function. Omega n is the system natural frequency or system frequency, and zeta is the system damping ratio. These are the system parameters. System damping ratio. It is zeta is a dimensionless quantity which is used for describing the decay of oscillations during a transient response. So it is the ratio of the actual damping to critical damping of a system. Zeta is basically a ratio of the actual damping to the critical damping. Now coming to this natural frequency, this is the angular frequency at which omega n is the natural frequency at which system oscillates in the absence of damping force. Next is the system damped frequency. This is again the angular frequency at which the system tends to oscillate in the presence of damping force. So the relation between these omega natural frequency and damping ratio and damped frequency is omega d is equal to omega n under root 1 minus zeta square. So this is the relationship between damped frequency and natural frequency and this. Now response of the second order system. Basically response of the second order system mainly depends on the damping ratio. For any test inputs, the response of second order system can be studied in 4 different cases. On the damping effect, we can, on the value of damping factor, we can define the type of the system. Now, the value of zeta may be greater than 1 or equal to 1 or in between 0 and 1. It may be 0, it may be 1, it may be between 0 and 1, and it may greater than 1. So on that basis we can define the type of the system. If the value of zeta, if the value of damping factor is greater than 1, then we call that system is overdamped system. If zeta is equal to 1, then that system is called as critically damped system. And if damping factor is in between 0 and 1, then that system is known as underdamped system. And if zeta is equal to 0, then that system is known as undamped system. So these are the type of the system on the basis of damping factor, and we can derive the responses of the second order system of all these systems, but we prefer only underdamped system because we can find more number of performance specifications in underdamped system. More number of performance specification means we can find more number of parameters of the underdamped system. If the undamped or critically damped or overdamped system will prefer, then we can't analyze the response of that system. So it will be difficult to find the different parameters of the system. So I will discuss this in the next lecture. Thank you.